So for the second talk, it's a pleasure to have Radu Silviu here who will tell us about on-shell diagrams for n equals 8 supergraph.
Thank you very much to the organizers for giving me an opportunity to speak here today. I'm going to present some recent work that I did in collaboration with Paul Heslop. And also you should pay attention to a talk by Jaroslav Trnka this Friday, which will also be on a similar topic, but maybe from a somewhat different point of view. Okay, so let me just begin with a very basic introduction for non-experts. Scattering amplitudes are the basic quantities that people use to compare theory with experiment. So it's of course a very important question to have efficient methods for computing them. But on the other hand, they also have a very rich mathematical structure, which is interesting in its own right, and that's sort of the aspect of the story that I'm going to be focusing on today. Now, the traditional methods for computing scattering amplitudes involve what are called Feynman diagrams, and these are a systematic and very intuitive way for computing scattering amplitudes. So here's an example of a Feynman diagram, and it's intuitive because one imagines sort of external particles coming in some way and interacting via the exchange of what's called a virtual particle. And so in principle, the problem of computing perturbative scattering amplitudes is solved. But of course, it's still a very active area of research. And the reason is because Feynman diagrams have some difficulties. And in particular, as the number of external legs increases, one finds that the number of Feynman diagrams that contribute to a given scattering amplitude quickly gets out of hand. Even though very often the final answer that you obtain is surprisingly simple. And sort of I think the essential reason for this difficulty is that the scattering amplitudes have off-shell states in the internal lines. Is because Feynman diagrams have off-shell states which are flowing through the internal lines, but scattering amplitudes only know about on-shell states. So when I say on-shell, what I mean is that the momentum squared is equal to the mass squared. So this is just a consequence of classical special relativity. But you can see, for example, in this diagram, that if you have two on-shell momenta here, momentum conservation tells you that the momentum flowing through this internal line is the sum of these two. And in general, the sum of two on-shell momenta will itself not be on-shell. So in general, you'll have states in the diagram that don't obey this condition, and in some sense they're unphysical. And so one of the lessons, I guess, that's been learned by the community that works on scattering amplitudes is the way to eliminate these difficulties is to use the analytic properties of scattering amplitudes in order to compute them without ever encountering such off-shell states. So in other words, you just pose the entire question in terms of purely on-shell quantities. Okay? In order to make on-shellness manifest in 4 dimensions, it's useful to use what are called spinor helicity variables. So in this talk, I'm going to be primarily focused on massless particles. So in other words, p squared is equal to 0. And it turns out for a massless particle in 4 dimensions, you can write its on-shell momentum in this bi-spinor form, where the indices alpha and alpha dot run from 1 to 2. They're sort of indices of SU2 times SU2, which is essentially the Lorentz group in 4 dimensions. And it turns out that when one expresses amplitudes in terms of these spinor variables, which make the on-shellness manifest, there are dramatic simplifications. And sort of the prototypical example of this is the tree-level amplitude for what are called MHV. Is the expression for the what are called tree-level MHV amplitudes. MHV stands for maximally helicity violating. And what that means is that you consider the scattering of gluons, and 2 of these gluons have negative helicity, while the rest of them have positive helicity. And what's remarkable is that no matter how many external legs you have in this diagram, at tree level, in the end of the day, the final answer can be written in this very, very compact form, where these brackets refer to inner products of the external spinors that are derived from the external momenta, contracted by this epsilon symbol. So the point is that for generic number of external legs, you have thousands of Feynman. I mean, the point is actually that the number of Feynman diagrams increases exponentially with the number of external legs. So there's no way that you can prove such a formula directly using Feynman diagrams for a general number of legs. So clearly there must be some more efficient way of doing things. And this method goes by the name of BCFW. It was developed by Brito, Cacciazzo, Feng, and Witten. And the idea is to simply deform two of the external momenta by a complex parameter in such a way that you preserve the on-shell properties. So for example, I'm going to choose to deform legs 1 and n. And the deformation looks like this. So I shift the lambda tilde 1 spinner, and I shift the lambda n spinner. And you can see that this shift preserves the fact that these momenta are still in bispinner form, so they're manifestly massless. And on the other hand, when you add these two momenta together, you see that their sum is invariant under the deformation, because this deformation comes with a minus sign here and a plus sign here. So the point is that I'm deforming these momenta into the complex plane in such a way that maintains the fact that I'm still working with an on-shell amplitude. And then the key observation is that for tree-level amplitudes, when you perform this deformation, they now become rational functions of this complex parameter alpha, which can in turn be reconstructed from their poles and residues. And so in particular, if the amplitude vanishes when alpha goes to infinity, this boils down to the statement that all of the poles will correspond to factorization channels of the amplitude, and at these factorization channels, the residues will correspond precisely to lower point on-shell amplitudes. And in this way, one can construct higher point on-shell amplitudes from lower point ones. So let me just illustrate this with a very, very simple example that I will return to several times throughout this talk. In this example, I'm going to consider a 4-point amplitude. So consider deforming legs 1 and 4 of this amplitude. So as I said, when you do that, we're considering a tree-level amplitude. It'll develop a pole in alpha, and at the location of this pole, an internal propagator will go on shell, and the amplitude will essentially factorize into two 3-point on-shell amplitudes. And you can see from momentum conservation that the momentum flowing through the propagator is just p2 minus p1 hat, where p1 hat is the shifted momentum. And so you see that the pole corresponds to the point, to the value of alpha for which p2 minus p1 hat squared is equal to 0. And as I said, at this point, or I should say the residue at this point, just corresponds to the product of two 3-point amplitudes. Now, instead of talking about a scattering amplitude, deforming it, and then sort of looking for the points at which, looking for the values of this deformation parameter at which the amplitude has poles and factorizes into lower point on-shell amplitudes, it's possible to implement BCFW recursion directly in terms of what are called on-shell diagrams, which were first developed for planar n equals 4 super Yang-Mills theory by this group of people. And n equals 4 super Yang-Mills theory is considered by many to be one of the simplest quantum field theories in 4 dimensions, because it has maximal supersymmetry, and it's certainly, at the very least, it's one of the most intensively studied quantum field theories in 4 dimensions. And the building blocks for these on-shell diagrams are basically just 3-point vertices, which correspond to 3-point MHV and anti-MHV amplitude. So this black vertex, it corresponds to the 3-point example of the MHV amplitude that I showed you on an earlier slide. And then you also have its complex conjugate, which is known as an MHV bar amplitude. And really the crucial feature that I want to emphasize is that for an MHV amplitude, one has that the lambda tilde spinners of each external leg are proportional, whereas for an anti-MHV amplitudes, one has that the lambda spinners are proportional. So if you haven't seen this before, just trust me, this is just a it's a very elementary consequence of 3-point kinematics. It's just pretty easy to prove. Okay. And then in terms of these on-shell diagrams, the BCFW recursion relations that I just described for you can be represented as follows. One simply sums over all factorizations into lower point amplitudes connected by what's called a BCFW bridge, where legs 1 and n are the two legs whose momenta are being shifted in some sense. And what's different, and then I guess really the key feature of on-shell diagrams that differentiates them from Feynman diagrams is that for on-shell diagrams, these lines do not contain off-shell states. So the rule one associates with one of these internal lines is simply an integral over on-shell states. And for the case of n equals 4 super Yang-Mills, this means integrating over the on-shell momentum, parameterized by the spinors lambda and lambda tilde, as well as a fermionic variable eta, which sort of takes into account the fact that you not only have gluons, but also scalars and fermions flowing through these lines. Okay, so again, just to give you a flavor for how this works, let me describe the 4-point example. So this is the on-shell diagram for a tree-level 4-point amplitude. Now, from the point of view of Feynman diagrams, this doesn't look like a tree-level amplitude at all. This looks like a loop-level amplitude. But the point is that because all of these internal lines are on-shell, in the end of the day, it will correspond precisely to a tree-level amplitude. So let's see how this works. So my two sub-amplitudes are going to be two 3-point amplitudes, which I'll denote by this black vertex and this lower white vertex. And then I attach them by a BCFW bridge. And then remember the rule that for every white vertex, all the lambda spinors are the same, and for every black vertex, all the lambda tilde spinors are the same. So that tells me that the null momentum flowing through this line must have a lambda spinor proportional to lambda 1, and the lambda tilde spinor in this line must be proportional to lambda tilde 4. And I'll take this proportionality constant to just be alpha. But then the point is that this proportionality constant can just be identified with the complex deformation that I described for you before. And then if you go back a few slides and you look at the precise form of the deformation, you notice that that's precisely equal to the momenta flowing through these deformed momenta 1 hat and 4 hat are precisely the deformed momenta that we saw in the definition of BCFW. And then the fact that alpha is being forced to land you on a factorization channel, again, comes from momentum conservation, because through this bottom at this internal line, momentum conservation tells you that the momentum should be P2 minus P1 hat. But because the internal lines must be on shell, this is putting precisely the same condition on alpha that we saw a few slides earlier from doing BCFW. So we see that this is really just a diagrammatic way of encoding BCFW recursion. Very good. On-shell diagrams are not just sort of a convenient way for doing calculations. They also reveal some very beautiful mathematical structure in the S matrix of n equals 4 super Yang-Mills. For example, they obey certain equivalence relations. One is known as the square move, which means if I have some internal square inside the on-shell diagram, I can reflect it along this horizontal axis or along this vertical axis, and that will leave the value of the on-shell diagram unchanged. And since this move looks very reminiscent of the Yang-Baxter equation, it's been suggested that this is somehow reflecting the underlying integrability of n equals 4 super Yang-Mills. Furthermore, you have what are called merger operations. So for example, if I have two black vertices connected to each other, I can merge them into an effective 4-point vertex and then unmerge them in a different channel. Same thing if I have two white vertices connected. Yes?
How much of this is true for usual Yang-Mills?
That's a good question. I think to answer these questions, you should look at a paper by Ben and Casa. So he in that paper he talked about how to generalize the on-shell diagram formalism to less than maximal super Yang-Mills, but in the planar sector. So I don't remember off the top of my head, so I don't want to say exactly, but there's a recent paper that explains this.
The flash direction is square move correct? Or
Sorry?
Are the flash direction correct in the square move? Or
Is the what direction?
Flash direction. Because you change once, but in horizontal one.
Well, yeah. This is an example where I'm reflecting, I guess, in the along the horizontal line. But there's also one where you reflect in the vertical line. Yeah. Good. Okay, good. So then you say, I just said that there are all these equivalence relations. So then the question arises, well, if I hand you two on-shell diagrams, how do I know if they're the same, if they're in the same equivalence class? And the answer is that they can be labeled by permutations. So in other words, the idea is that I go in from one external leg, and then for example, I take a left when I hit a white vertex, and I take a right when I hit a black vertex. And in this way, I'll eventually emerge at some other external leg. And so this maps the external legs into themselves. And so in that way, you can assign a permutation with the on-shell diagram. And then the claim is that this permutation is unaffected by doing these equivalence relations. And furthermore, it turns out that they're also in one-to-one correspondence with what are called positive cells of the Grassmannian. And ultimately, this gives rise to some very beautiful geometric interpretation for scattering amplitudes. As the volume of some abstract object, which eventually obtained a very interesting name called the amplituhedron, and sort of one of, I guess for me the interesting the interesting aspect of this story is that one can somehow see the emergence of basic physical principles like positivity like locality and unitarity from more primitive geometrical principles like positivity. And furthermore, n equals 4 super angles in the planar limit has another nice property known as dual conformal symmetry, which I won't really have time to explain. But it turns out that this provides a canonical definition for the loop integrand, making it possible to actually extend this recursion relation to loop level, that is at the level of the loop integrand, because the loop integrand is also a rational function. And schematically, the way one does this is to add in another term to the recursion relation where you take two external legs, adjacent external legs, and you connect them, and then you place a BCFW bridge immediately outside of that. And schematically, what is going on here is that I'm introducing some complex deformation, and now the statement is that if I tune it to the right value, I'm in some sense putting the momentum of an internal propagator on shell. Good. So this is obviously a very beautiful story, but it's also for a very special theory. So of course, a natural question is, how to generalize these ideas beyond planar n equals 4 super Young mills. And in this talk, I'm going to describe how to do this for n equals 8 supergravity, which has been argued to be actually the simplest quantum field theory in 4 dimensions, just because it has even more supersymmetry than n equals 4 super Young mills, and it also has a nonlinearly realized E7-7 symmetry. And although n equals 8 supergravity probably doesn't make sense non-perturbatively, because its non-perturbative completion should be M theory on a 7 torus, it's still an interesting open question whether it's perturbatively finite. Because if it is, it's certainly unclear what would be the underlying symmetry or dynamics that would give rise to perturbative finiteness, although some important hints are provided by color kinematics duality. And so the fantasy, I guess, that I'm pursuing here is to actually use on-shell diagrams to perhaps deduce an all-loop integrand for n equals 8 supergravity, analogous to the all-loop integrand of n equals 4 super Young mills, which I would think provide some insight into the question of perturbative finiteness. And also perhaps to use them to sort of generalize the notion of an amplituhedron to a gravitational context, which I think would be profound. But these are very distant fantasies. In fact, in this talk, I'm primarily going to talk about tree-level amplitudes. And although BCFW was already established for gravitational theories long ago, it turns out that reformulating BCFW in terms of on-shell diagrams will actually reveal some interesting new structures and some surprising, or at least surprising to me, relations between n equals 4 super Young mills and n equals 8 supergravity. And some examples of these will be sort of non-planar identities that actually allow us to recast the computation of n equals 8 supergravity amplitudes in terms of planar n equals 4 super Young mills amplitudes. analogous equivalence relations at the level of on-shell diagrams of n equals 8 supergravity, and also Grassmannian integral formulae. And moreover, this Grassmannian structure that I'm going to describe will allow us to deduce a simple algorithm for actually just reading off the formulae of on-shell diagrams. So in other words, just reading off expressions directly from the diagram. So this is a very requires, I guess, very little amount of computation and is also very easily automatized. And finally, I'll briefly speculate about the extension of these ideas to loop level, and I think Yaroslav will probably have more to say on loop level amplitudes on Friday. Good. So let's just proceed naively. So just like in n equals 4, you say that your building blocks are going to be 3-point amplitudes. So in this case, the 3-point MHV amplitude, it has the following formula, which is essentially the square of the 1 for n equals 4 super Yang Mills. And this white vertex is the 3-point anti-MHV amplitude. And for every internal line, again, I just say that corresponds to an integral over on-shell states. And the main difference between n equals 8 and n equals 4 is that now I have a d to the 8th rather than a d to the 4th because I have twice as much supersymmetry. But it turns out that naively applying BCFW does not get you the right answer. It turns out that in order to get the right answer, you actually have to decorate the BCFW bridge. So in other words, one has to use the following definition for the BCFW bridge. Is equal to the standard one, or at least the one that appeared in n equals 4 super Yang Mills, times a prefactor of 1 over p1.pn, where p1 and n are the two legs that are being shifted. And there are different ways of anticipating this. One is just from dimensional analysis. When you compare the on-shell diagrams to the supergravity amplitudes, you see that they're off by something of mass dimension -2. And so this is certainly the most natural thing you can write down. But of course, you can explicitly prove it just by matching the on-shell expressions you get from on-shell diagrams for a general factorization channel to that of standard BCFW. But anyway, and if you just use this decorated version of the BCFW bridge, then BCFW recursion takes the following form. So once again, you sum over all factorizations into lower point subamplitudes left and right, connected now by a decorated BCFW bridge. But unlike n equals 4 super Yang Mills, the gravity amplitudes are permutation symmetric, so they're intrinsically non-planar. And so one actually has to sum over all partitions of the particles 2 through n minus 1 into the two sets left and right, while holding legs 1 and n fixed. So just to make this more concrete, let me describe some simple examples. So the first example is just the 4-point amplitude. In this case, we just have a decorated BCFW bridge. Otherwise, it's exactly the same as the on-shell diagram that appears in n equals 4 super Yang Mills. The only difference is that now we have to sum over the permutation of legs 2 and 3 because we put the bridge between legs 1 and 4. Very good. Now things get slightly more interesting at 5-point because there are different ways to proceed. For example, if I choose one of the subamplitudes to be a 4-point amplitude, and I take the two legs that are being unshifted in the 4-point amplitude, and I use them, I feed them into the diagrammatic recursion by connecting them either to the BCFW bridge or to the other amplitude, then what happens is that I sum over permutations of 2 and 3 coming from the 4-point amplitude that I just described. And in the end, the entire amplitude, 5-point amplitude, just comes from taking this planar diagram and summing over permutations of legs 2, 3, 4. So essentially, in the end of the day, what I'm left with is a sum over planar diagrams. But you could do something else. You could attach the 4-point amplitude in such a way that one of these unshifted legs is connected to the BCFW bridge, but the other one is left as an external leg, rather than attaching it to the other amplitude. And in this case, because I have to sum over permutations of this leg and leg 3, I'll get a non-planar diagram. And so in this alternative choice of recursion, I get a sum over non-planar diagrams. But this implies a very non-trivial identity between sums of non-planar on-shell diagrams and sums of planar ones. And this story actually generalizes to any number of legs. You can actually show by induction that if you always insist on using the unshifted legs of each subdiagram as the ones that you feed into the recursion, then the result you obtain will always be a sum over planar diagrams, which are exactly the same planar diagrams that appear in n equals 4 super Yang-Mills. So the punchline is that you can actually obtain n equals 8 supergravity amplitudes simply by taking planar on-shell diagrams of n equals 4 super Yang-Mills, decorating them, and summing over permutations of unshifted legs. And then that's a little bit surprising, I think. But on the other hand, if you were to choose to carry out the recursion in a different way, you will generically get non-planar diagrams. And as you go to higher and higher legs, this implies some very non-trivial identities, which could potentially have application, for example, if you want to compute non-planar Yang-Mills amplitudes using on-shell diagrams. Very good. And furthermore, it turns out that the on-shell diagrams of n equals 8 supergravity also obey analogous equivalence relations. So just like for n equals 4, there's a square move for n equals 8. So this somehow suggests that maybe there is some kind of Yangian type symmetry in n equals 8 that's responsible for the finiteness, although that's very speculative and probably overly provocative for me to say. But you also have the analog of mergers. The difference is that in order for these mergers to work, you need to decorate opposite edges of the diagrams. Without these decorations, you'll get funny factors of spinor inner products. So it seems like more or less the problem of computing n equals 8 supergravity can be reduced to the problem of computing amplitudes in n equals 8 supergravity can be reduced to the problem of computing amplitudes in planar n equals 4 super Yang-Mills, but including decorations. And so that makes you think that perhaps many of the structures that you saw in planar n equals 4 super Yang-Mills can be carried over to n equals 8 supergravity. And in fact, the answer turns out to be true. It turns out to be yes. And not only does that sort of give the n equals 8 supergravity amplitudes a beautiful geometric interpretation, it also sort of gives an efficient way to do calculations. So what I'm going to do now is describe an algorithm for reading off expressions for on-shell diagrams in the form of Grassmannian integral formulae. And such structures also, of course, played a prominent role in the scattering amplitudes of n equals 4 super Yang-Mills. And so before doing that, perhaps I should actually define what I mean by a Grassmannian. So the Grassmannian GRKN you can think of as the space of k-planes in n dimensions, or equivalently, you can think of them as the set of k by n matrices modulo the left action by GLK. And in the context of scattering amplitudes, k will correspond to the helicity degree, and n will correspond to the number of external legs. And then given a k-plane C, it's also very convenient to define an orthogonal n minus k-plane C perp. So more explicitly, you think of C as a k by n matrix, and then you have this matrix C perp that's an n by n minus k matrix, and they satisfy the condition that when you multiply them together, it vanishes. And this basically determines C perp up to an overall normalization. But then you can fix that normalization just by demanding that the k by k minors of C are equal to the n minus k by n minus k minors of C perp. Very good. So to see how this works for n equals 8 supergravity, first let's start with the example of 3-point amplitudes. And I'm just going to write down what the Grassmannian integral formulae are, because they're really not that difficult to guess. You see that you have these parentheses just correspond to minors of the C matrices, and for an MHV amplitude, the Grassmannian is G2 comma 3, and for an anti-MHV amplitude is G1 comma 3. So for MHV amplitude, you're integrating over 2 by 3 matrices modulo GL2, and for an anti-MHV amplitude, you're integrating over 1 by 3 matrices modulo GL1. And then it's not difficult to see that these just reduce to the formula I wrote down a few slides ago by using the GL symmetry to fix the C matrices to very obvious forms. So in particular, for the MHV amplitude, if you use the GL2 symmetry to set this C matrix just to be the matrix whose 3 columns correspond to the 3 external spinors participating in the amplitude, you see immediately that these minors just reduce to spinor inner products. And so you get a 1, 2 squared, 2, 3 squared, 3, 1 squared, just like we saw appeared, just like we saw appeared here. Okay. And similarly, you find that this delta 4/16 just reduces to the supermomentum delta function. And furthermore, this ij over ij just cancels out, because as I said, the minors are just equivalent to the spinor inner products for this choice of C. Now this is very similar in some ways to the Grassmannians that one writes down for 3-point amplitudes in n equals 4 super Yang-Mills. Basically, you can obtain these from the n equals 4 super Yang-Mills one by taking the denominators and squaring them. But what's a little bit novel is the appearance of this explicit inner product, ij. And a non-trivial fact is that this object is permutation invariant. So it doesn't matter which pair of particles I'm talking about. The value of this thing will be the same no matter what. And sort of the appearance of this explicit inner product is signaling the fact that n equals 8, that gravity is not conformal. So one way to derive these formulae, actually if you're an expert on twistors, is to actually start with the 3-point amplitude in momentum space, Fourier transform it to twistor space, and then Fourier transform it back, and that gives rise to what's called a link representation. And when you do that, you find that you're forced to introduce an infinity twister. And that's essentially reflected in the presence of this spinor bracket. And similarly, for the anti-MHV amplitude, you will have you have the complex conjugate spinor bracket, and this minor ij perp is actually a minor of C perp rather than C. Okay, so you have some interesting looking structures here. But of course, there are many choices of coordinates one can make for these Grassmannians, and it turns out that there's a canonical choice of yes.
Geometric interpretation for those expressions? Are you computing something geometric by those things together?
Well, yes, it's a good question. I think yes, but I'm not really sure. I would hope yes, but I'm not really sure. For example, the whole story of positivity, at least for these guys, carries over. So the point is that all of this positivity that appeared for planar n equals 4 super Yang-Mills also carries over to undecorated planar subdiagrams of n equals 8. But the thing is that after you sum over permutations, that interpretation is spoiled. So I think the answer is yes, but I don't really have a crisp answer, a concrete answer to what it would be. So it turns out that there are other choices of coordinates that you can make for the Grassmannian, and a canonical way to do them, a canonical way to assign coordinates on the Grassmannian can be realized by assigning arrows and variables to the edges of the on-shell diagrams. So for 3-point amplitudes, this choice can be displayed as follows. So for a black vertex, I'm going to take 2 of the external legs to have incoming arrows and 1 to have an outgoing arrow. And for a white vertex, I'm going to have 2 of the legs to have outgoing arrows and 1 an incoming arrow. Okay? And then I'm just going to assign a variable to every edge of each vertex. Then in terms of these edge variables, you can determine what the C and C perp matrices are using the following rules. Okay, so essentially it boils down to summing over paths through your on-shell diagram. So for the C perp matrix, you start. Sorry, for the C matrix, you start with an incoming leg, and then you just follow the arrow through to the end of the diagram, and that gives you a relation between the lambda tilde spinor on that internal leg and the lambda tilde spinors on the other external legs, simply by keeping track of all the alpha parameters that you pass through along each given path and multiplying them together, and then summing over all possible paths. So for example, in this black, this is a trivial example. So for this black vertex, if I start from the leg 1 and I follow the arrow through, I exit through leg 3, and in the process I pick up alpha 1, alpha 3. Okay? And so you see that the C matrix has an alpha 1, alpha 3 in it. Okay? Similarly, if I start with leg 2 and I pass and I follow the arrow, I get a factor of alpha 2, alpha 3, and indeed I get this factor of alpha 2, alpha 3 in it, in the C matrix. Similarly, you can deduce the C perp matrix by following the paths in the opposite direction. So to compute the C-perp matrix, I start with an outgoing arrow, and then I follow the arrows backwards. And then, once again, I just sum up over all paths. For each path, I multiply together all the phases that I encounter along the path, and then that gives me a relation between the lambda spinner on this outgoing leg and the other lambda spinners on the other outgoing legs. And using that approach, you can deduce the C matrix. So, for example, let's talk about, in the case of the black vertex, there's only one outgoing leg, leg 3. When I go outwards, it bifurcates. I get leg 1 and leg 2. Okay, so I see that lambda 3 has to be a linear combination of lambda 1 and lambda 2, and that's precisely what is being said in this matrix, right? So in particular, lambda 3 is equal to alpha 3, alpha 1, lambda 1, plus alpha 3, alpha 2, lambda 2, and that's precisely what this C matrix says. So if you compute the C matrices in this way and plug them into the covariant formulae that I showed you a few slides ago, you get the following very interesting structures. So in particular, you see that for the black vertex, I get a product of external spinners, and these two external spinners correspond precisely to the two legs that had two incoming arrows. For the white vertex, I get a square bracket of spinners. These guys correspond precisely to the two legs that have outgoing arrows. And then you see some interesting powers of the alphas in the denominator here. And the reason why this is a useful exercise is because it turns out that this structure generalizes to any on-shell diagram. So from our experience, with these 3-point amplitudes, one can write down a general algorithm for writing down expressions for any on-shell diagram in terms of these canonical coordinates, which can then be lifted to covariant Grassmannian integral formulae. So let me describe the algorithm. Let me sketch it, I guess. So step 1 is to draw an arrow on each edge such that there are always 2 arrows entering a black vertex and 1 leaving a black vertex, and similarly 2 arrows coming out of a white vertex and 1 entering a white vertex. Then you label every edge by a variable alpha, and you can set one of these variables to 1 for each vertex. Then you can associate a d alpha over alpha squared with every edge variable which is leaving a white vertex or entering a black one, or a d alpha divided by alpha cubed with each edge variable which is entering a white vertex or leaving a black one. So this just to make this clear, what's going on here is that for a black vertex, you have 2 incoming arrows and 1 outgoing one. So in this example, if alpha 3 would be the measure for alpha 3 would be d alpha 3 over alpha 3 cubed, but the measures for alpha 1 and alpha 2 would be d alpha 1 over alpha 1 squared and d alpha 2 over alpha 2 squared, respectively. Okay, so the point is that for the special arrow, you have a 1 over alpha cubed. For the non-special arrows, you have 1 over alpha squared. Okay, very, very simple. And then finally, for every black vertex, you associate a angle bracket, ij, where I and j are the 2 edges with ingoing arrows. And for every white vertex, you associate a square bracket, ij, where I and j are the 2 edges with outgoing arrows. And then you just determine C and C perp using the path summing procedure that I described 2 slides ago. So to make all of this very concrete and to sort of illustrate the power of this approach, let me again describe our favorite example of the 4-point tree level amplitude. Okay, so this is what we're going to do. First, we're going to start with an undecorated 4-point on-shell diagram. Okay, the full amplitude will of course come from decorating one of the edges and then summing over a permutation of the opposite edges, of the opposite legs. Okay, and then I can just assign 4 edge variables in this way. And using the rules on the previous slide, you easily see that the measure from these edge variables is just 1 over alpha 5 squared, alpha 6 squared, alpha 7 squared, alpha 8 squared, because in each case, the arrow is pointing in a non-special direction, so to speak. Then for the white vertices, I get the square brackets associated with every outgoing arrow. So for example, for this white vertex, I have bracket 6, 7, right? And that's what I have here. For this vertex, I have bracket 8, 5, and that's what I have here. And then for the black vertices, I have angle brackets, spinners, right? So angle brackets. So in particular, for this vertex, I have 7 and 8. Very nice. And for this vertex, I have 6 and 5. Okay? And then I have delta functions in C and C perp. And these delta functions can be read off directly from the on-shell diagram simply by following the paths and multiplying all the phases that I encounter as I follow through. Okay? So it's all quite easy. Okay, then you can also use the path prescription to write these internal brackets in terms of the external spinors. So for example, you can see immediately that lambda tilde 5 is equal to lambda tilde 2. How do we see that? Well, let's look at lambda tilde 5. If I follow this arrow outwards, I go to lambda 2. Okay, but let's choose a less trivial example. So for example, lambda 5 is equal to alpha 5 lambda 1. How do we see that? Oh, wrong direction. So if I start with lambda 5 and I work backwards, you see I hit lambda 1, but I pick up a factor of alpha 5 in the process. So if you go through this for all of the internal spinors and you plug that back into the expression I had on the previous slide, what you find is that each of these brackets has an alpha in it. And so you have 4 alphas, which cancel out 4 of the alphas in the denominator, and then I'm left with a d-log form, just like in n equals 4 super Yang-Mills. And furthermore, you can uplift this to the following covariant formula simply by computing the minors of C, and then just guessing, you know, what minors you have to put in here to get the right GL weight. And you see that it's very similar to the Grassmannian integral formula of n equals 4 super Yang-Mills. You have this Park-Taylor-like denominator. The difference is now that you have these external spinors coming in the game, divided by minors. And the point is that which legs I choose to appear in these spinors and the minors, it doesn't matter. It's invariant for any choice of legs. It's the same for any choice of legs. Okay, so now to complete the calculation, what I have to do is divide by a bridge factor and sum over permutation. So in this case, I'm going to decide to put a bridge here between legs 1 and 2. So that means I'm going to divide by the bridge factor 1, 2, 1, 2. That's sort of the inner product of the momenta of legs 1 and 2. And I sum over the permutations of legs 3 and 4. And when you do that, and you use the Schouten identity at the level of the minors, you get the following very interesting looking Grassmannian integral formula. And this is for the full 4-point n equals 8 supergravity amplitude. So this is sort of the analog of the Grassmannian integral formula that one obtains for planar n equals 4 super Yang-Mills. And you see now I have a sum over all pairs of legs, so it's not just the Park-Taylor formula. So this is a manifestly cyclically symmetric formula. And again, these terms are also cyclically symmetric. So this is an interesting structure. I think that there's a lot to be said about it, but yeah, I mean it requires some thought. Good. And of course you can go to higher points. If you're interested, you can see our paper. But I think this should be enough just to illustrate the basic idea. So let me now just conclude with some speculations about loop amplitudes. Now, in principle, it's not clear that there's a canonical way to define a loop integrand for non-planar theories, and in particular gravitational theories. But on the other hand, there's some very interesting recent results, for example, from the ambi-twistor string, that suggests that such an object may exist for supergravity theories. Let me just say that there's some encouraging evidence that this recursion relation can be extended to loops, because if you just follow the logic that seems to apply at tree level, if you just apply that to loop level, you actually will get the right 4.1 loop amplitude. So in particular, if I just take the on-shell diagram that appeared in planar n equals 4 super Yang-Mills, which described the one loop 4-point amplitude, and I just add decorations to it, and then I sum over permutations of the external legs, this thing actually gives you the correct one loop 4-point amplitude of n equals 8 supergravity. Although, to be honest, I don't think we have a systematic understanding of why. So of course, it's a very important question to do more examples and see, you know, whether this is sort of a coincidence that appears at 4-point, which could be, or whether this is a structure that actually generalizes to any number of legs. I would hope that it does. Good, and I guess I should finish. Let me now just finish up by describing some future directions. So obviously, I think the most urgent question is whether this recursion relation can be extended to the loop integrands, and I think really the only way right now to address that question is to work out more examples and see if some pattern emerges, and you know, ideally one would like to make a claim that you could compute loop amplitudes in n equals 8 supergravity essentially by decorating the on-shell diagrams of planar n equals 4 Yang-Mills and summing over permutations, but that may be too optimistic. But of course, another interesting question is the relation of all of this story to twistor string theory. And I should actually say that that was the original motivation for studying n equals 8 supergravity amplitudes using on-shell diagrams, at least for me. So in particular, there are also some Grassmannian integral formulae that were inspired by, or at least I guess derived from a twistor string theory that was developed by David for n equals 8 supergravity. These things are rather complicated looking, and it's not completely obvious to me how these are related to the ones that we deduce from on-shell diagrams. So I think that would be interesting, worth clarifying. But I guess another interesting question has to do with computing loop amplitudes in supergravity theory. So this has been done successfully at one loop and perhaps higher loops for 10-dimensional supergravity using an ambi-twistor string framework. And then there's been some work on what's called a 4D ambi-twistor string, because it's intrinsically four-dimensional in the sense that the target space consists of spinners. And there the status of loop amplitudes is less clear. And part of the difficulty was that there wasn't really a natural structure to match onto. But as I said, because the target space of the 4D ambi-twistor string consists of spinners, the types of formulas that you get out of amplitudes that you get out of it are very reminiscent of the types of formulas you get from on-shell diagrams. So I think, with some expression, on-shell diagram expression for the one loop 4-point amplitude at least, in terms of it may be interesting to. I think it may be interesting to revisit this problem. And then, as I said, the big difference between gravity and Yang-Mills is that gravity is intrinsically non-planar. So many of the issues that you would encounter if you want to, for example, compute non-planar amplitudes in Yang-Mills theory, you're forced to address when you compute amplitudes in gravity. And so I think it's an interesting question to see how much of the story, or how many, to what extent the ideas that seem to be arising in the context of n equals 8 supergravity can be adapted to compute non-planar amplitudes in Yang-Mills theory using on-shell diagrams. And I think I'll end there. Thank you.
So you explained that to go to gravity from Yang-Mills, you have to decorate on-shell diagrams. Can this be understood as a double copy construction or not?
That's interesting. Yeah, I don't completely. I mean, certainly at the level of the 3-point amplitudes, they're double copies, right? But the level of these full on-shell diagrams, it seems I don't really see the double copying. It seems like it's somehow an orthogonal point of view. But yeah, I think that would be interesting to understand. I mean, it's not really that you're sort of squaring n equals 4 on-shell diagrams, at least at first sight. But maybe somehow these decorations that you're putting in amount to squaring the amplitudes. Although I don't completely see how.
Are your tree amplitude expressions simpler than the ones that were gotten before, or are they more?
I don't think that they're necessarily simpler. I think that they're equivalent. And they're in a very different form. So in the sense that they have this Grassmannian type form, and that wasn't really I mean, the fact that you could write down a Grassmannian integral, well, I mean, certainly there are these Grassmannian integral formulae that were deduced from twistor string theory. I think they have a very different flavor, or a different character, and it would be interesting to understand that. I think sort of, in the end of the day, I mean, I think all of these formulas are the same. Of course, as the ones that have been deduced in the past. I guess the virtue of this approach is that it reveals some new structure. The on-shell diagrams reveal some new structure. Number one, they reveal new, I think, somewhat unexpected relations to n equals 4 super Yang-Mills that I think may have some deeper implications. Number two, and also I think, at the level of computation, it's kind of nice, because there's actually very little computation that needs to be done. Literally, all you do is draw diagrams using the recursion relation, and in fact, you can just borrow all of that from n equals 4 super Yang-Mills at tree level, and then you just decorate them, and then you just you just assign canonical coordinates, and you just read off expressions. This is something a computer could do, and there's really very little explicit calculation. It's literally just drawing diagrams, and reading off expressions to some extent. And
Easy to see the MHV is simpler than the non-MHV in this approach?
Yes. Yeah, and in that case, the Grassmannian integral formula that you write down will involve a non-trivial contour in the Grassmannian. So in other words, for MHV amplitudes, all of the alpha variables are completely localized by the delta functions, whereas for non-MHV amplitudes, naively they're not. So you have to impose some non-trivial contour on them, and that contour will essentially come directly from assigning canonical coordinates to the on-shell diagram. Mm-hmm.
So I've got a rather naive question, I think. What's the physics behind this square move, both in n equal 4 or in n equal 8? Is that some redundancy of the formalism, or is it purely implied?
Yeah, that's a good question. The physics, yeah, I mean, at some level, the way you see it is just by computing it explicitly and seeing that it's invariant under these moves. If you look at the original paper on on-shell diagrams, they somehow argue that this is related to integrability. But on the other hand, you see it appearing in n equals 8 supergravity, which isn't really known to be integrable in any standard sense.
What happens if you compute it on both sides? You're playing the same results, and that's it essentially.
That's right. I mean, at 4 points, at 4 points is just so the kinematics is so simple that you have this square move.
Okay, so it's in higher point diagrams that it becomes somehow.
Right. Yeah. I'm not sure. That might not be a satisfying answer to your question. But on the other hand, it may be a deep question, or it may be a pretty non-trivial question. So, yeah.
That formula you had for the 1 loop 4 point gravity amplitude.
Mm-hmm.
Does that somehow mimic the cut constructible?
Yeah, so I guess, okay. So there's a whole story, I guess, relating on-shell diagrams to what are called leading singularities. And these leading singularities basically correspond to residues in these alpha parameters that I talked about. So in this case, you can see that this diagram has manifestly correct leading singularities, because what happens is that when I set these external alphas to 0, that effectively turns off the momentum flowing through those edges. So I can effectively just erase those edges. And then when I do that, what I'm left with is just the 4-point tree on-shell diagram that I described earlier. And then that is precisely just equal to the 4-point tree amplitude of n equals 8 supergravity times STU. So that's what you would get, in other words, by looking at the explicit formula for the 1-loop amplitude of n equals 8 supergravity written as a box, in terms of boxes, and then cutting all of the four propagators in those boxes. Yeah, so I mean, I guess at 4 points it's not difficult to guess what you should have. But actually deriving this systematically from an on-shell diagram recursion is non-trivial, because in principle when you do it, you see if you look at the recursion relation for planar n equals 4, what you do is you take two adjacent edges and you connect them, and then you just attach a BCFW bridge to the edges immediately outside of them. But for n equals 8, because it's a non-planar theory, in principle one should connect this BCFW bridge in many different ways, in particular giving non-planar diagrams. And so in addition to this planar diagram that you would naively get, you also get, in addition to this planar diagram, you would also get a whole bunch of non-planar ones, and the question is, do these somehow in the end just sum to some planar object, or should you for some reason not have included them when you did the recursion? I guess that's sort of the aspect of the story that really needs to be understood. And at 4 points, it's difficult to extrapolate to higher points, because 4 points is so special. So somehow I think the only way to address it is just, as far as I can see right now, is just to do a 5-point 1-loop or a 2-loop 4-point and see what happens. And then in the end of the day, you can come back and have some beautiful story about why it should be this way. But at this stage, it's difficult for me to say.
Okay, so we'll come back at 11:30 and resume with Bobby's talk from earlier, but let's thank Arthur again.